Are you ready, guys?
I am.
Yes.
Here we
Let's
go.
do it. Good.
You want to start?
Yes. Hello, everybody. Welcome to our third webinar. I'm Jochen. I'm the Director of Water Treatment globally, and I have here my colleagues working together with a great team here.
Yes. Good morning, good afternoon, good evening, everyone. My name is Philip. I'm a Managing Director here, responsible for Scotland and the American, Asian, and Australian markets.
Yes. Good morning, good afternoon from my side. My name is Dominic. I'm beside Philip, the other Managing Director. We are a huge company. This is why we have two.
We need to, yeah.
And it's great that we have so much people who are following us, and we're trying to make a good session now about what?
We look into drinking water treatment, pathogens removal, and heavy metals. That's the key topic today.
Exactly.
Yes.
So we are today more in the drinking water area, huh?
Exactly.
Groundwater, surface water. Okay, let's start the presentation.
Yeah, where we have over 75 participants. I think it's time to start. Huh?
Time to start.
Okay,
you just joined at the right moment.
Okay,
quickly,
I just mentioned already, we go into some biology of sandfill, as we do every time that we have a good start. We look into THMs removal, pathogens, iron removal, and then some case studies.
Yes.
Yeah.
Okay.
One comment to this. Maybe I apologize that we bring always this biology of sand filters, but we have to because we want to use this on our YouTube channel as a standalone presentation. So all of you who follow all the 4 seminars, of course, it's quite repetitive.
Yeah.
Apologize for this, but for the standalone version, we do it. It's the key one.
Yeah.
Okay.
And it doesn't hurt to hear this 2 or 3 times.
Not all.
Really,
not at all.
Okay. Good. So ground rules. You have an option to participate through your Q&A function. Please use this to ask your questions as we go through the presentation. We will be recording the show here, so it is available on our YouTube water treatment channel for you to review after we publish it later today.
So for all the people who follow us for a long time, we had the Dryden Aqua YouTube channel. Now we split it in 3: Dryden Aqua Pools, Dryden Aqua Water Treatment, and Dryden Aqua Aquariums and Aquaculture. So that would be the water treatment channel. Please subscribe on this. All the new videos you will get, and make the alarm button.
Yep.
Then you always get an information if we have a new post on it.
Exactly.
Okay.
Yeah, you're
Good.
You're the YouTube champion here.
Yeah. There's a LinkedIn channel, by the way. Yes.
Yeah.
You are the LinkedIn.
Yes.
I'm more the YouTube guy.
Yeah.
Okay. We need to share the work.
So let's
YouTube pays better.
First, before we jump into biology again, let's just quickly give you an overview of Dryden Aqua. So we are working in 3 different business areas. The company actually started out in aquaria and aquaculture some 30 years ago, driven through Dr. Howard Dryden. This today is still part of our business. It's about 10% of our total sales.
At that time, it was called Dryden Aquaculture. We cut it now to Dryden Aqua.
Exactly. And then about 12, 15 years ago, we started to push into the swimming pool segment, which today is still our largest segment with about 50% of our sales. And then a few years ago, we started to push and invest into the much bigger and, much more important also water treatment segment. Huh?
And when we started this, nobody wanted to listen to us.
Yeah.
Remember the first Aquatech?
Yeah.
You said, okay, we are coming back in 2 years and see if you're still alive.
Exactly.
And then we started with some small orders, but now we have Jochen in our team, and his goal is, this is your objective.
Yes, these filters you see, these blue big ones, to fill them, yes.
Yes, to fill them, and to bring this to the dominant sector in our
So today this
portfolio.
Is already about 40% of our business.
Yeah, and we want to bring it to 80.
Yeah. Good. Okay, where are we? We have, as you may know, we have 2 production facilities. Our Scottish facility, where we can make about 25,000 tons per year. Our Swiss operation, which, by the way, you can see this here in the background a little bit.
So behind here, this is the big sieve, the beast, as we call it.
And together we can produce about 55,000 tons of AFM per year. We also have an office in Germany, logistics space, mostly responsible for Eastern Europe and Russian markets. We have a sales office in the US. We also have a logistics space with 5 warehouses in the US. And we have an office in Shanghai in China for the Chinese market.
With one warehouse.
With one warehouse, correct.
Yeah, that's where we are.
Yep.
Okay, let's show you 2 minutes, one of our production, and this is the newest that we have, the most sophisticated, that's Switzerland. 2 minutes, we will be back. Okay.
Okay.
So I really love this video. I love this factory that we have. Yeah, you have seen, it's not just green what we are producing, the AFM. It's really, we use very green technology with solar power and rainwater and sludge that goes to biogas. So sustainability is very, very important for
Absolutely.
us. And, yeah. And we call it, by the way, it's a little bit like Tesla.
Yeah.
It's a little bit like Tesla. Huh? It's fully automated. Well, it's not a gigafactory. It's maybe a mega factory, but it's really good. And if you ever have the chance to come to see us in Switzerland or in Scotland, call us, write us an email. We are very happy to welcome you and to show you all this.
Exactly.
Okay. That was it.
So,
biology of sand filters.
Biology. That's one of your favorite topics, huh?
Yeah. And I'm economist from my education, so I all learned this from Dr. Howard Dryden. Now let's talk quickly about bacteria. In all water we have bacteria. We have heterotroph and autotroph bacteria. Heterotroph bacteria are feeding from organics and produce inorganics. Autotrophs are just the opposite. Heterotroph bacteria can double if you have nice conditions, enough food, warm temperature, like at 30 degrees, they can double every 30 minutes. So this really goes exponential. Autotrophs are doubling at a much lower rate. They double every 10 to 12 days. Let's start with the heterotroph bacteria. Main species is the Pseudomonas. You can call them the pioneer. They're in the water and they want to survive. So maybe there is oxidants like chlorine in the water. So what they do, they immediately look a surface which is in contact with the water, where they attach to this surface and they encase themselves in a mucus. What? Mucus?
Mucus, yeah.
Extra polymer substances, EPS.
So that's what most of the water treatment people here around, what they understand about the cover, the slime.
Okay. So I apologize. So in pools, we just call it a biofilm. You know, these bacteria attached to the surface, covered with this slime, this mucus. Mucus or mucus? Mucus. This slime, you know, this is what we call a biofilm.
Yep.
And then they grow, they double, and this biofilm becomes thicker and thicker, more and more stable, and more acidic as well. And this biofilm is quite resistant against chlorination because chlorine cannot penetrate the biofilm. It has to oxidize from outside to inside, and by this, you're losing concentration. So even with high chlorination, you will not be able to remove 100% of the biofilm. You will have 1, 2, 3 survivors, and these are the very strong bugs, right? The survival of the fittest, who are very good in developing, again, that biofilm to protect themselves.
Yeah. So like Dominic said, you know, bacteria will attach on surfaces that are in contact with water. So what's important to understand is when we talk about sand in these systems, sand is, one, a natural breeding ground for bacteria, and two, it's also by far the largest surface that is in contact with water, because 1 meter cube of sand has approximately a surface of 3,000 square meters. So very easily, the sand can be 90–95% of the total surface that is in contact with water.
Yeah. Absolutely true. And yeah, we know all sand, good mechanical filter, but they also will start to become a biofilter. In agriculture, we use fluidized sand beds as biofilters to grow bacteria, and also some sand filters. I remember, especially IDE in Israel, they use sand filters as a combination of biofilter as well as mechanical filter.
Exactly.
But it's a compromise solution. As you all know, compromise solutions are not the best solution. It's better to make first this and then this. Okay, problems?
So, so biofilm itself, what is the problem with biofilm? What happens in the sand filter is over time that the biofilm leads to coagulation of the sand grains. So they will start to stick together and they form lumps. They form clumps in the filter bed, and ultimately this will lead to channeling of the filter bed. Now, based on the application, this can start sooner or later. We see this usually starting after about 3 to 6 months when this can happen.
Can be 12 months, depending also very much on the temperature, on the load, on the backwash velocity that you can achieve. But if you have channeling, you know, then you don't have any more reliable filtration. Then you have highways which are going through your filter bed. So you bypass the media. You bypass the media. You don't have any more filtration. And very often you see, you know, that this biofilm, these colonies are discharging into the water. It's when your water becomes really cloudy and where it will end up on your membranes. That was last session that we discussed. Or you have pathogens like crypto, you know, where you don't have any more 1 micron filtration, where you have 20 micron filtration. We'll see that later on. And this is not good. This is, and you see this especially when turbidity increases. You have much more suspended solids and biomass, which is discharged into filtered water. Your filtration is not any longer reliable.
So you start seeing these spikes in turbidity, you know, if you look at the filtration profile over time. Now, what's important, I think, here is that initially with fresh sand, you will have a good filtration, a reliable filtration, but this problem starts after some time.
Yeah, when the autotroph bacteria are moving in, because they're producing organics, which is the food source for the heterotroph. So this is when it becomes a lot more dynamic. Let's go to the next one. Now, of course, you can try to solve that problem with hyperchlorination, shock chlorination, etc. And it helps always a little bit. But the best is you avoid it. And you do this with a bioresistant filter media. And the very best that I know is AFM.
Okay. So why and how is the surface of AFM self-sterilizing? what happens is a catalytic reaction on the surface of the grain. This is when dissolved oxygen in the water reacts with metal oxides that are part of the AFM grain, that are on the surface of the grain, that will react, and they will form free radicals. You can click a couple of times, to see the animation.
Water, and you have the oxygen here, two
exactly.
ppm dissolved oxygen minimum, and then you form these free radicals.
Yes, and these free radicals have a very high oxidation potential, higher than chlorine, for example. They only live fractions of seconds, but this is enough to oxidize bacteria that are trying to attach on the surface.
So these guys want to move here on the grain size, but that doesn't work.
Yes.
You're gone, you're oxidized.
So in order to have a self-sterilizing surface, you need two things, right? Really, you need a glass type, which is the green and the brown glass, which contains chromium oxide and iron oxide, which is necessary for this catalytic reaction. You also need an increased surface, and this is what we do with our activation process, because this is a surface reaction. The more surface you have available, the more of these free radicals you will produce.
Yeah, and they only stay on the surface area. They don't discharge to them.
Exactly.
Yeah, they're very, very short-lived. It's a small amount, but it's enough to protect them. But here you see also the DNA of Dryden Aqua, and especially of Dr. Howard Dryden, you know, as a biologist, let the problem not come. You know, with sand, you let it come, and then you try to solve it with a lot of oxidants, etc. Howard, as a biologist, he goes the way, let's not get to the problem.
Let's prevent it, huh?
Yeah,
yep, exactly.
Okay, let's come to AFM. You know, for 20 years, we had AFM, and it was AFM. Now we have two types of AFM, AFM standard, and since 2 years, we have on the market AFM NG, which stands for the next generation. Both of these AFM are bioresistant. Both of them have a huge increased surface, but there are some differences.
Mm-hmm. Yes, there is some key difference of them. Yes, for example, negative surface charge, important. AFM standard has a negative surface charge, very important. Here we can remove cationic charged particles, especially heavy metals. So this is really the benefit if you use AFM standard, absorption of heavy metals. That's the key property of our negative charged AFM standard.
So mainly iron, manganese.
Iron, manganese,
arsenic.
it can be arsenic, can be removed quite efficiently, yes.
And that's a problem in many groundwaters. Arsenic is a lot in Bangladesh. There is some in Greece. I think also Italy, Spain. Iron you have everywhere.
Groundwater, manganese, iron, that's a big problem anywhere, yes. Arsenic spread around the world, yes. Of course, large surface area, as you mentioned before.
Yeah. And it's really good filter media, very good filter media, filters down to 4 micron. So that's really great.
Yeah.
So what's the difference to NG? Why did Howard do the NG?
So why did he NG? So first of all, what's the difference to the standards? AFM NG next generation has a hydrophobic surface area. So what does it mean? So hydrophobic surface means it can remove organic particles like microplastics, proteins, oil, and lipids. So the main reason for development was to remove microplastics.
Yeah, that was his mission. You know, microplastic is hydrophobic. It doesn't love water. And this is why he developed the AFM-NG, because with a hydrophobic filter media, you can easily remove hydrophobic particles. Mm-hmm. And when we tested it, and it really works fantastic. I mean, much, much, much better than AFM standard. And when we tested it in our very, very fancy test lab, we also found out works very well against with proteins, with oils, and with lipids.
But not to be too fancy, we can even show you in a simple picture here.
Yeah, here up you see AFM standard, which is hydrophilic, it loves water. And below we see AFM NG, the hydrophobic, it repels water, it doesn't like water. Mm-hmm. And by the way, it's also for us easy to show really the activation process, because some people said, well, I don't believe in it. It's just marketing here. Our 3-step activation process, 2 chemical steps and 1 thermal steps. By the way, I see we had 2 hand raises. We have seen you. Maybe we take you to the end. Because otherwise people want to leave maybe after 1 hour. So you're not forgotten. Raise your hands again at when we come.
Please use the Q&A if you have any questions. We will go through them.
Or raise your hands and come live. That's absolutely good. But we do it in the Q&A sessions.
Okay. So what do you need to know about the difference of these two products, really? If the key thing is with AFM standard has a negative surface charge, which makes it very good at electrostatically attracting positively charged particles. These are mostly metals, like we mentioned it, iron, manganese, arsenic. So that's the main application for AFM standard. For AFM NG, Jochen mentioned it, it has a hydrophobic surface, which means it works very well with other hydrophobic substances like organics, like hydrocarbons, for example, like microplastics, and with a, anywhere between 30 to 50% higher performance compared to AFM standard.
Yeah. Today, honestly, we use 90% NG. AFM standard makes an excellent job. It was very good. It is still very good for many, many years. But, the better is the enemy of the good, right? And but really, where AFM standard is superior is in the heavy metal removal, which is obvious.
Actually, you can combine these two if you want to.
Yeah. You can make a mix 50-50, and you have both.
Exactly. Okay, so we were talking about performance and how well it is. Now you can believe us, or you can believe some independently verified tests, which of course we have done with a French institute. What's the name of that institute?
IFTS.
IFTS.
And it stands for Institut de Filtration et Technique Séparative.
Très bien, merci beaucoup, Dominique.
Bien sûr.
Very good. Okay. So, and what you see here, these are the results. So on the horizontal, you see the particle size in microns, and on the vertical axis, you see the removal performance in %. So we lay the minimum threshold that we want to achieve at 95% removal.
Yes, standard of IFTS, by the way, is 80, but 80 is not good enough for us, and 90 is not good enough. So we said, let's put the limit on 95.
Exactly. So what you can see on the left side, the 1 micron filtration, you can see AFM NG grade 1, removing 95% of all particles down to 1 micron. You can see AFM standard grade 1 performing at 4 microns,
which is a huge difference.
Which is absolutely.
I mean, here it's quite similar, but here in the 1 to 4 micron, it's huge difference.
Yes. And then you see on the right side or in the middle, you see sand. This is a high quality fresh sand that performs at 20 microns. Now, what's the difference between 1 micron and 20? It's 19 microns. Is that a lot?
That's actually a lot, yeah. I mean, many people don't know that it's a galaxy.
It's a galaxy of difference. We know that.
And there's a lot of particles which are smaller in your feed, in your water feed. Yes.
Yeah. Now, we also tested some glass medias that we do not show here. All of them were less good than sand. This is why we took sand. Keep in mind, especially sand will go down in the performance with the biofouling. And you can find this on our website. This IFTS reports, a summary of it. Yeah.
A word about grade 0?
Yeah. You take this?
Okay. So you can also see that we have a grade 0.
This one here.
This is only available as a standard product, not an NG, because we cannot make it hydrophobic. I guess we could.
No, it's
but there's
blocking the nozzles.
It would block the nozzle.
We haven't managed this. So
very high performing filter media, 98% down to 1 micron.
And because our particle size analyzer and also the one from IFTS stops at 1 micron, we can't tell you where we will scratch the 95 threshold. I guess it's 0.5 and not below.
Wow. So where do we use grade 0?
Yeah, grade 0 is quite often used, for example, in seawater desalination as a top layer to remove very fine clay or silt particles. Yes.
Yeah. Okay. So if you want to go in hyper filtration, ultra, we don't call it ultra. If you want to go in a very, very fine filtration, we use it. Or if we have existing installations where we cannot backwash higher than 30 meters per hour.
Yeah. Maybe one more thing. Sorry, I don't think it was mentioned. These tests were done at 20 meters per hour filtration velocity, which is very high
for water treatment.
Water treatment.
Pools are 30. Water treatment usually is 10. So we took the middle 20. Each of these tasks cost more than 5,000 euros. So I mean, we have our data for sand and for AFM for different filtration velocities that you also find in our IFTS. In our IFU.
Almost like it's
IFU, everything.
Our handling manual for AFM.
And it was 1 meter of filter bed. One word to backwash. This is very important. You know, filtration is a 2-step process. You filter and then you clean. And it's really important that you clean it properly. And to clean it properly, you need to have a bed expansion of minimum 15%, ideally 25 or higher, to bring the particles to the top of the filter bed. And to fluidize this filter bed, if this is sand or AFM, you need a certain velocity. This will depend on the water temperature. The warmer the temperature, the more velocity you need. This also depends on the size grain and the shape. Now let's assume sand and glass, in our case AFM, has exactly the same size and the same shape. Because sand is 20% heavier than glass, you need 20% more of backwash velocity in order to expand the bed.
Should we show the video quickly, how the filter bed expands? Right?
So here, maybe you have never seen this because usually your filters are not transparent. Here, this is an IFTS, Institut de Filtration et Technique Separative.
Wow, look at better.
Sorry, I trained it this morning. And here you see this bed expansion that we have here. You know, slightly it's starting to expand. You see how you have the expansion, how the solids are brought to the top.
It's impressive to see how these particles are removed.
And this is how it should be in your filter. And therefore you need a reasonable hardware. I always call the filter the hardware and the filter media the software. You also need, especially if you have heavy particles, such as heavy metal that we see later on, you need a certain velocity, you know, to have enough of shear forces to bring them not just to the top of the filter bed.
Drag forces, yes.
Drag forces, okay, to wash them out. So sand usually needs 40 if you have 0.4 to 0.8 millimeter to 60 meters per hour backwash velocity. If you have 0.7 to 1.2, and AFM, you know, depending on our grade 1, grade 2, between 30 to 50. But we really need this bed expansion.
So we like the high speed backwash.
Short and fast.
Short and fast
is better than long and slow when it comes to backwash.
Yes. When it comes to backwash. Not in every...
I mean, and we have seen installations where they backwash for 30 minutes with that very low velocity.
450 to 20.
And this is crazy.
You will never be able to fluidize the bed, and you will remove few of these particles, maybe 10, 20, 50%, whatever, but not more. And I had a lot of discussion on the different aquatecs where they said I have an existing installation. I can only backwash at 10 meters per hour. I filter at 5. Where we do not touch these projects, where we say, no, we can't do it. I mean, it will work perfectly for 4 weeks, but then performance goes down. It's really important. A filter is like a bin. You have to empty this bin from time to time. So our backwash velocities, we have in the pool sessions, we explained this in detail, how you do this and in what time, or we did it in the first session, right?
Yeah, we did some more explanation in the first session, but also the pool academy is really a good learning experience.
But, let's stay on water treatment. So we did in the first session, so you can review this. A last point, which is really important, you know, in sand, you, especially if you're bigger filters, you need air purge. You really need this. And why do you need this? Because you want to rip off the biofilm from the sand grains. And air purge is doing this, only maybe 95%, but it's doing this job. We don't have this biofilm. This is why we don't need air purge. So you can save the blower on the capex. You can save this operation cost.
Energy,
we don't need that. You can do this, not with the NG, but with the standard, but we don't need
I guess that can be quite a significant saving, huh?
It is a significant saving,
Exactly.
Okay.
So here, this is how it looks after 3.5 minutes. So this is more or less what you need, huh?
Backwash curve.
Yes.
So we also have in our IFU handling manual, you can see that we just take a couple of slides out here to show you here grade 1 bed expansion, grade 0 bed expansion. They have quite different expansion depending on the velocity you run through the filter. So that's why it's important. We always want to have a minimum of 15 bed or 20% bed expansion. So that's why it's really important that you take care about your bed expansion using our filter media, that we can achieve a good backwash velocity.
Yeah.
First for expansion, secondly, also to remove all the particles, yes.
Yeah. So you find this in our IFU, in our manual. Usually it will be a mix, you know, here, for example, you see a 50-50 mix where we have at 30 meters per hour, we have 15%, that just works. Usually here we would like to have a higher backwash velocity, like 40 meters per hour. Yeah. If we are below 30 meters per hour, as you can see here, we only would be, you know, at 5, then we compensate this by adding some grade 0.
Yeah.
Please come to us, maybe not for the projects with 200 kilos, but everything above 20 tons, we're happy to consult you, you know, especially in the first 2-3 projects. If you have done 2 projects, you know it by heart. But
yeah.
However, we are here, especially Jochen. He has also a very nice calculation tool, which is not online yet. It's still in the
We're still working on it,
phase.
yes, but it looks quite nice. Already using it with our projects.
Yeah,
beta version, huh?
I think that's the last for backwash.
Yeah, exactly. So this is key and important. We just summarized it before, but here again, visually explained. So please, for heavy metal removal, we need to have a higher backwash velocity to really remove these heavy particles, because they will go against the natural gravity. So you need to have a good drag force, and that's only achieved with high speed backwash.
Yeah. And if we have this 40-50, we would go here for a 50-50. Otherwise, we get too high of bad expansion, especially if the water is a little bit colder, and we would lose media.
Exactly.
To lose a little bit of media is okay. You know, the fines that you have, you know, this 5 to 10%, this is okay. This is like with the whiskey. We call it the angel share. But then it should stop.
Yeah, exactly. So this is the most important document, the IFU instructions for use. Go to our website, click on downloads, and you can get the most up-to-date version.
So we have imperial version and we have a metric version.
Exactly.
Okay, this was the theory before, and now we come to the practice.
Yes.
Yeah, half an hour. Let's quickly talk about chloroform and THMs in general, and chloroform.
Okay.
You know, yeah, you want to take this?
Yeah, I'll do. So how are THMs being formed? This is something that happens mostly in chlorinated systems where, you know, large chain organic molecules are being chopped down by chlorine, by hypochlorous acid. And chlorine will continue to chop them down into the smallest organic molecule there is, which is a methane.
Yeah. 1 carbon, 4 hydrogen. Yeah,
exactly. Also, UV can cause a breakdown of organics.
Yes. And then chlorine will continue to react. This is what's called a substitution reaction, I believe, right? Substitution reaction, where some of the hydrogens are replaced with chlorine. And this continues until we have a chloroform or a trichloromethane. So three chlorine atoms and 1 hydrogen and 1 carbon.
But the key one is, to form chloroform, you need 2 things. You need chlorine and you need organics. So if you remove 50% organics by better filtration, you have 50% less of THMs.
Exactly.
Yeah.
Exactly.
So you use AFM.
Usually you can, use AFM. This is exactly what we are doing.
And then we also have a solution to deal with THMs to some degree, but like you said, prevention is the key.
One word to the health issues of THMs and chloroform in this case. It's very volatile. As you can see here, Henry constants 185 bars, very volatile. The gas is out. If you breathe it in, it goes in your lungs. It goes through your lungs in your bloodstream. It's attacking your nerve system. It's cancerogenic, and it was the first anesthetic. You know, the more you breathe in, you're not getting smarter by doing this. It's a little bit like alcohol, I guess. Well, we have more experience with alcohol than with
THMs.
Honestly, I do not know how big is the problem, you know, to drink water when you have chloroform. I do not know.
Big of a deal,
but I know that just when we joined Dryden Aqua in 2012, Dryden Aqua had a nice order of 3,000 air diffusers to strip off chloroforms in all their reservoirs. And work absolutely perfectly. Okay, let's move to pathogens in water systems. And okay, I start with the Pseudomonas. I already explained you these bacteria. These are the pioneers. These are the guys who are building up the biofilm, and then a full species of other bacteria and microorganisms are moving in. If they are alone, planktonic, that means like this, you kill them very easily. With 0.13 chlorine, you kill them. It's very, very easy. But the moment where they are protected with the mucus, with the EPS.
EPS, yeah.
With the
wow.
EPS.
With the EPS.
Yeah,
that's actually what you see in the middle of the picture here. The middle picture shows this EPS.
The EPS. Okay,
yeah.
Good. Excellent. Then they become very resistant. They are quite small, not easy to filter. So we are, with AFM, not filtering them really. We avoid that they can grow. This is the key one. Self-sterilizing surface, no biofilm, that means no Pseudomonas.
Yeah. Okay. So the next pathogen that is commonly found in surface water is Cryptosporidium.
Milwaukee, 1976.
Yes. So, which is responsible for diarrhea, vomiting, and so on. It's of fecal origin.
Yep.
The bad news about crypto is it's highly resistant to chlorine. So it can survive at 5 ppm chlorine for 5,000 hours. So it basically
that's long.
It basically can't be killed with normal chlorine dosing, right? The good news, however, is it's relatively big in size. So it's 3 to 6 microns in size. And you remember AFM-NG with its 1 micron filtration makes AFM very good at removing, 99% plus of Cryptosporidium simply through filtration.
In one pass.
In one pass.
And crypto is not nice, it's I think it's the most, you have wrote it, the most common waterborne disease. It also has a mortality roughly, I think how it mentioned 1 to 400. So this is more than corona, right? It's not good. It's also not easy, with the chlorine, as you already mentioned, but also with UV, because it's captured. Actually, if you really would have one, a CPM after the filter to crack off the crypto would be good. But that's no good in this.
Then
E. coli.
Another one, of course, we have a couple of different bacteria. E. coli is one of the famous one, actually is usually many times used as a bacteria indicator. So in many drinking water treatment plants, this has been measured to show if there's anything growing, which is like direction going to E. coli. So it's also fecal bacteria. You can see here in this little animation, it grows quite quickly. In a couple of hours, it becomes quite big, 5 micron, but usually it's small, between 0.2 and 1 micron, 2 micron long. And of course, again, like with many other species, it comes in through animal waste, entering river, lakes, and groundwater. Again, as we mentioned before, if you have no growth, mainly from Pseudomonas bacterial layers, you also avoid the attachment of E. coli, and that also reduces your potential growth or release of higher concentrations of E. coli.
Yeah. Absolutely. And maybe one word back to this, even if you say, well, I have a sand filtration, I do coagulation, flocculation, I filter down to 1 micron. Yes, all perfect until your filter is channeled. Remember the highway, then you can flocculate, coagulate as much as you want. They go through. Okay, last but not least, Legionellas. There are about 70 different species of Legionellas. 60 of them are completely harmless, not a problem. 70 of them can be dangerous, especially the Legionellas aeruginosa. Not if you drink it. You can drink thousands, millions of it. It's not a problem, but if you inhalate them, then you can get Pontiac fever or this Legionnaire's disease. And if your immune system is not the strongest, it's a good chance that you will not survive it. They grow usually in water temperature between 25 to 45. It's really a problem in cooling towers. I mean, in pools, we have some problems with it, in spas, but here it's really a problem with cooling towers. And we can avoid it with our self-sterilizing surface. Philip, do you lead us through this, how that works?
So, and obviously, like you said, if it's Legionella is always an indication of biofilm. right? So if we have, it's, you know, this is what we experience in these cooling towers.
So you can have Legionellas, you know, just in tap water also, or in biofilm, but it's really, they grow, they double in biofilm.
So what Dominic mentioned, the Pseudomonas, they are the pioneers. So they are responsible for the formation of biofilm. Next, amoebas are moving in. So amoebas, they look for the protection of biofilm. These are relatively big animals. These are pathogens that move in. And then what happens is the Legionella, they actually like to be absorbed, taken in by amoeba because it protects them. And the amoeba cannot digest them. So Legionella will grow and multiply within these amoebas until they burst. They explode, and then
they release a lot of
millions or thousands of Legionella at one point will be released.
I never counted them. I think it's more sizes. However, but that's their mechanism to grow. But that means, as a consequence, if you have AFM, you don't have Pseudomonas, you don't have amoebas. Only can live in biofilm. So if you don't have a biofilm, amoebas cannot live. So no biofilms, no Pseudomonas, no amoebas. No amoebas means no or significant less of Legionellas and many other microorganisms that we
the key is no biofilm.
Key is no biofilm, and that's why bioresistant filter media, right?
Okay,
surface water,
AFM and surface water treatment. Let's take a look at some installations.
Some case studies.
So here's a picture. This is from our friends from India, Nikunj. I'm not sure if you are on the call, but this is an RGF installation in India that was done years ago, actually together with Howard also. Howard was on site. So Nikunj, we would love to get an update on this with some more results. We haven't seen anything in a couple of years.
I heard from Howard it's working very fantastic. Well. And as Nikunj is placing always new orders, I guess it is. But we are missing data. And that goes to all of you. I mean, you ask us, do you have data? Do you have case studies? Do you have reference points? Yes, we have, if you give them to us, right? But surface water, very often gravity filter in India as well as in Switzerland. Newest project from you, Jochen.
Actually quite recent. So only 3 weeks ago, we started this plant in operation. It's in Zurich.
It's not yet in operation.
It's not. It started operation. Actually, to be honest, 3 days ago we just started with this. But 3 weeks ago we filled this in here. It's I'm quite proud of that. Very nice installations, like in India, but now also in Switzerland. So this, as you can see here on the right picture, it's near Zurich. And we have here the big lake, and the water is taken out of this lake. Of course, the lake is already quite clean. So this water, you almost can drink it from the lake, but of course, that's not drinking water. So we need to...
Not in Switzerland.
Not in Switzerland. In other countries, you may even drink it directly.
So what was the process? Or what is the process?
So the process here is we take the lake water. It's treated by just directly with filtration. They add some coagulant to it before, so they have a regular coagulant dosing, and they want to overcome that problem of coagulant dosing, meaning they want to reduce the cost, they want to reduce chemical use, so they were looking for the best filter media. So the best filter media they found with AFM. They replaced all these media, sand, anthracite today, and they run today at 6 meters per hour, like before, and 25 meters backwash velocity. So really, that's perfect. In our case, we really achieve a good performance, I expect.
Yeah, this water still goes through ozonization and think even carbon filter, right?
Afterwards. So after filtration.
These guys, they used to replace the sand every 5 years, and we do not have yet the regulation or the approval or the certification for the SVGV for Switzerland for drinking water. You know, you have to do in each country an individual one. It's a long process, also not a cheap process. But this operator, he said, I want to have the best, I believe, in AFM. And he has watched our video that you have seen in the beginning and said, this is fantastic what you're doing. This is really sustainable, and this is why I want it. So sorry, we cannot share already the results with you. We will have the first results maybe in 2-3 weeks. And then, of course, we have to let it run for 1 year, you know, really to show really the difference. But what is your estimations?
Yeah, let's see their estimation. First of all, why they want, as you mentioned, they want to have the best filter media because they want to reduce the coagulant or stop coagulant dosing. They, of course, expect to improve even the water quality, which I'm sure we are doing it. And of course, we have no air backwash. As we mentioned before, we stopped the air backwash here. So they are not using any more air backwash. So that's an energy saving and operating and maintenance savings costs for them in the future.
Yeah, we also, I think we cut it down his backwash times quite dramatically.
Yes,
right?
we cut it down from around 20, 25 minutes total backwash, including air scouring and so on, to around 10 minutes at the moment. Yes. Yeah. So we're still optimizing, but it will be around 5 to 10 minutes backwash every couple of days, once a week around. What do we achieve here? So we expect here.
What do we expect? It's not tested
exactly,
yet.
It's not taken. Yeah. So
but we are confident with this.
Yes.
So green is the hope. Huh?
Yes. It's not only hope, it's a belief.
No,
yes.
Absolutely.
It's a belief. Yes. So turbidity, it's already very low in the feed water, as I mentioned before. It's 0.5. With sand, we reached today about 0.2, but we achieve definitely we will be below 0.1.
I'm sure it will be beyond detection level. I think detection level is 0.05.
Yeah. Typically they write less than 0.1. That's below detection level.
Yeah.
Yes.
Yeah.
Exactly. So cell count, they do a regular cell count, 1.6 million. With sand, you maybe cut it to half, but I'm sure because no biofouling, much better filtration properties, we will be below 500,000. Actually, I think we will be much more below, but
that's very conservative.
Kind of then other mesophil bacteria typically also measured. There will be some remaining in the sand. We will definitely have much less in with AFM. Color, that's maybe not so important here, maybe not really related to the removal here, but that's also removal which we may achieve with some removal of organics.
Yeah, I love this project because it's first one in Switzerland and we are Swiss. And what I really like, this guy, he said, I don't care.
I don't too much.
I don't care about the regulations. I do it. And of course, the health authority will now overview check
control,
this in a much more regular base. And it will be perfect. Yeah. This is the Hall of Fame. This is to show, that we are not just talking, we also have hands-on experience. Here what you see, in Switzerland, because labor force is very expensive, we have special trucks. They are not, you don't own them. There are special trucks that you load here with big bags and then you blow it in with water, etc. And then you flatten it and maybe you recognize this gentleman here.
Oh, it looks like very close, very similar to me. Yes.
Yeah, absolutely.
So I'm not only talking like here in front of the video and then doing some nice home office or office work. I'm also hands-on helping our customers.
Good. Yeah. Good. You also will enjoy in the next coming weeks to help us here in the production. Yeah. That's another hands-on experience.
Learning experience now.
Yeah, absolutely. This is what Philip and me will do tomorrow. Instead of going to the fitness, which costs a lot of money, we help here in the production, and this is good. Yeah.
Okay, maybe one thing to add here, because you mentioned the certification in Switzerland, right? Yeah. Every country is different. And of course, and I think you talked about this in the last slide, but very important to know is that AFM comes with NSF 61 certification for drinking water. It comes with DWI. So in many, many countries, you can go ahead with AFM and you're fully covered. From a certification
but not yet
perspective.
in Switzerland, not yet in France, not yet in Germany. Usually this is what is called the European Union. You have to go in each and every country and do this exercise. I was getting the wrong word.
Wasting exercise.
It's kind of new piracy.
Here's another great example, a case study that we got from our friends Hoimyang in Korea. This is a project Hoimyang in South Korea that was done 9 years ago. This is for river water makeup water filtration for cooling towers. So they had, very typical problems. They had high TSS coming in. They had high demand for chemicals, biocides, and so on, right? So what our partners did, they developed, and you can see this here. This is a fairly simple, straightforward process. Taking in the river water and going straight into the AFM filters for the makeup water production. They were using grade 1 and grade 0 for this project. And Yes, as a result, you can see they were able to bring down turbidity by a factor of 20, from 10 to 0.5.
Which is good.
Which is
from 10 to 0.5.
Absolutely.
That's good, yeah.
They eliminated biofouling in the filter. So basically the bug count, the bacteria count was dramatically reduced.
Down to 100, factor of 100.
Down to 100, yes.
Suspended solids.
Suspended solids, of course. Yeah. So excellent results. This has been going on now for 9 years, still generating great results.
Okay, let's come to a very important subject, iron, manganese, and arsenic removal. I mean, as long as these metals are in solution, you cannot filter it. So I know when you joined us a year ago, you knew only one way to bring them out of solution.
Of course, usually the oxidation chemicals are used. Chlorine dioxide, potassium permanganate are used to remove or to oxidize heavy metals in water before they are filtered out, yes. And so you convert ferrous to ferric, from 2 to ferric 3. So that means from dissolution, from solution to be undissolved. So that's the way you can remove that out of the water, yes.
Yeah. So you have to do this, and then you will remove AFM from nearly any concentration below 0.01 milligrams per liter, which is great. There's a second one, and this is aeration. Again, this is Howard, trying to avoid chemicals. And if you just aerate the water for 30 minutes or longer, and you use the perfect air diffuser, you do the same thing. And by chance, we are also manufacturing since 30 years, not we, Dryden Aqua is manufacturing air diffusers.
So this is one example, the 1.3 meter, they come in 10 different lengths. The longest is 3 meters, which is by far the one that we sell the most.
Which is good for 10 cubic meters of water per hour. Yeah, you can zoom, Philip, a little bit.
You can see it's flexible, it's heavy, so it drops down to the bottom of the tank or the lagoon. It doesn't need to be bolted to the ground.
Very easy to clean. If you clean them, you can go on and run the system.
Exactly.
But the very, very beauty is, now you're big.
Yeah.
Good.
Okay, so here you connect it to the hose, which is connected to the blower. And again, they come in different length.
Yeah, and also we have an instruction manual with all the details how to install it.
Absolutely.
And they are not the cheapest on the CapEx, but definitely the cheapest in the OpEx, because the oxygen transfer is massive. It's 20 to 30% higher than any other air diffusers. And we show this next week in our Bangladesh experience.
Maybe we make a special session about
why
this.
Not? Why not? Yeah, good. Okay, back to the presentation. That was very good, Roger. You're getting better and better. I love this guy. I don't have control. Maybe you tip once in. I like to have control.
Today you control, actually.
So by aeration, what you do, as Philip said, or Jochen said, the ferrous you put into ferric oxide. And the ferric oxide has a very high redox potential on the surface has a very high redox potential. So it's very easy to oxidize this iron to ferric just with half an hour of aeration, with good aeration, using our air diffusers, the one that you see below. Manganese and arsenic is a lot more difficult. Here you have two options. Either option one, if your iron content is 5 times higher than your manganese or your arsenic, you have such a high, with the high redox potential and 5 times more of this ferric, you will also oxidize the manganese Mn2 to Mn4 and As3 in As5. Both are solid particles.
Yeah, arsenic to arsenate, yes.
Yeah, arsenic to arsenic and manganese to manganese dioxide.
Perfect,
manganese oxide. I'm not a chemist, but I'm learning here. This is good. Live learning, as you do.
So this is what we call co-precipitation. Through the iron, you co-precipitate the manganese and the arsenic.
Did you read it here? So if you don't have this, you have two possibilities. You can add ferric chloride to the water to increase it to this level. So maybe you think this is quite stupid. You know, I have an iron problem and even add more iron. It's not. It's really a very good one because you do not have to remove later on the oxidants, the chlorine or the ozone or whatever. If you don't have this possibility, you have to use the oxidants to go to a redox potential higher than 500. Okay.
Of course, yes. You can also do it. You have other benefits with aeration.
Yeah. What are the other benefits?
So first of all, aerating the water is kind of stripping out volatile products. So methane, hydrogen sulfate, actually very often the case in different locations worldwide.
Chloroform.
Yes, chloroform as well. Yes, VOCs. Of course, then you do at the same time you stabilize the alkalinity and the pH. This gives you a much more stable water quality.
I think that's very important because that really gives much better filtration also.
Yeah, exactly. Filtration is improved, water is stabilized, and you increase the oxygen level, which we like for our AFM for the self-sterilizing properties to be even more efficient.
Because that could be a problem. You know, if you take it from groundwater, quite low, where you have zero oxygen, to take it up, it can be that the AFM is not anymore bioresistant because you have zero oxygen. You need 2 ppm of dissolved oxygen in the water in order to create the self-sterilizing surface. So we love aeration.
Absolutely.
It's also really important you drop the zeta potential, so you also start, that's another benefit, you also increase the coagulation reaction or the coagulation properties in the water. And coagulation and flocculation properties are also improved.
And all in a natural way.
Everything in a natural way.
Good.
Okay.
Other things to, you want to take this, Philip?
Yeah, I mean, how does AFM compare to other filter media that are on the market for the same purpose? And we choose 2 here that are the most common that we see.
Berm, you see always in South Africa.
And we have manganese, green sand. They are both aluminum silicate products.
Mainly used in Europe and the United States.
Exactly, that have, manganese dioxide surface, right? And this generates a catalytic reaction, like we just mentioned, to precipitate these metals.
A little bit like our ferric, right?
Yeah, exactly.
You oxidize Mn2 to Mn,
Yes. So these are reliable products, but they also have their downsides. So we just want to mention 2. One of them is that the filtration performance, so if we talk about particle removal, doesn't even get close to the performance of AFM's 1 micron filtration. We're talking 50, 60, 100 microns in particle size. And secondly, these products need to be recharged. They need to be replaced at some point. So there is some OPEX, and some maintenance.
Yeah, and also the stability of your operation may drop. You don't recognize it early enough, so you will not have a constant good operation. And you need pre-filtration in both of them. Yes.
But to be clear, you can use them. There's no problem. I know my friends in South Africa, they also love to sell it. I'm never against selling, as you know. End of the day, I'm a businessman. They do AFM filtration. They used to do sand filtration followed by berm. Now they do AFM filtration followed by berm. If you do it with aeration, you can do it in 1 step. So it's up to you. If you say, no, I like this repetitive sales business, I have full understanding for you. And I'm sure also you, Philip, you can do it. You can do it in both ways. Our solution, obviously, is 1 step AFM together with aeration.
Exactly.
Yeah. Summary?
Okay, summary, AFM compared to sand. Again, suspended solid removal is just a galaxy better when we compare AFM to sand. Bacteria removal, sand is bioactive, so it's not applicable, while AFM is bioresistant, so we have much better performance there again. And then iron manganese removal, we just discussed this. Sand has basically no impact on sand and manganese removal.
Very little. There is an impact, but that's why it only has 1.
Exactly.
I don't know how you call it.
Check mark.
Check mark. Okay.
Check mark, yes.
Compared to 4.
Exactly.
We have to speed a little bit up,
Yeah,
and
okay.
groundwater, maybe 2 other case studies. This is one from Spain. Quite old, by the way. It's also roughly 8 years old. 200 cubic meters a day, and here the other village, 400 cubic meters a day. Yeah, here you see the filters that they used. There is few things that you could improve in the process. They also did aeration and a little bit of oxidation because they didn't use our aeration.
Higher amount of iron.
Yeah, it was high amount of iron. They used also some oxidation because their aeration system was quite poor, to be honest. But you see here turbidity factor of 10, not as good as we have seen before in some young. Arsenic factor of 4 below the level, the WHO level, and iron from 5 to you said always below 0.1. Here we are 0.14.
Yeah, okay.
That was wrong, but I think we can accept. We can live with this. And the same goes here with the other village. And we also have these approvals. One which is a lot more impressive is the one that we showed in the first one. This is Square pharmaceutical company. Groundwater pre-treated before RO. They had huge problems with iron. They had huge problems with turbidity and huge problems with Pseudomonas. They had sand filtered, followed by carbon filter, activated carbon filter, followed by cartridge filter. And our partners from BioVista in Bangladesh, hi guys, you're great. They made a very nice installation here with Colplus filters. Project installation was done by colleague in Italy. They did a fantastic job, fantastic engineering job. It's 2 hours of aeration, filtration velocity only 5 meters per hour. I mean, you can't do it better. And look the results that they achieved from 10 to 0.03. I mean, you can go that low, but if you do it such a good job as our friends in Bangladesh did, and then you see also turbidity, Pseudomonas just gone.
So no biogrowth, yes.
No, no. Yeah.
Okay, here's an example from China. This is a large brewery project completed in China. You can see the filters, 3-meter filters. The problem here was that the piping was way too small. These were DN100 pipes. And, if you look at a 3-meter filter, you would need 7 meters per second pipe velocity to properly backwash that filter. This is impossible. This is why we
2.7.
Yeah. And we couldn't change that. So the backwash was 20 meters. That could not be changed. So we decided to go with grade 0 for this project. Carbon filters were removed after changing over from sand to AFM.
And again, here we don't have results. We just heard from our Chinese partner. They are very happy. Okay.
Yeah.
They're very happy. But we are happy, to be a supplier in the brewery industry because, share a secret with you, we quite love beer. That's another beer here. That's a beer in Ireland, a black beer, quite a famous one. I do not want to mention the name. They used to use tap water to brew the beer, but then the tap water becomes too expensive, so they decided to go for groundwater. And there was a big famous French company who did the project, and it did not work. So finally, these guys went to Irish partners, much smaller company, who together with Dr. Howard Dryden, found a solution. Main problem here, again, groundwater. Not a lot of iron, but huge amount of manganese in the water. Huge amount of manganese in the water. We changed it to AFM. Honestly, they had to change the piping here and the backwash pumps because they were much too low. And because we have heavy metals, we wanted to have 45 meters per hour of backwash velocity. They can't do aeration. Also, it would not help because there is no iron in it. So they oxidize the manganese with chlorine dioxide, and after the filter, they remove it here with UV before they go in the RO system. Again, here, we don't have any numbers, but I heard from Howard that the payback of this project is not years, it's months. Yeah. And I like this beer. We are not only in beer, mainly we are in beer. We also have 2 customers, one in Djibouti and one did he is a German one,
Kliva, yes.
who did a nice project for a sweet water. It looks a little bit like the beer, quite black, but it's sweet, quite famous. In Ethiopia, this was delivered in October. They promised to install it in February and to send us the results.
Yeah,
so,
I think they install it in March. So we're still pending the information. But
yeah, Mr. Müller, if you're on the call, here we are. We are waiting on you, or at least on your results. Huh?
Good.
But to operate all of these applications in drinking water and in food and beverage industry, as we just talked about, we have the so-called HACCP, food safety certified. So our production is producing according to HACCP. And of course, as you mentioned, Philip, before, we also have NSF drinking 61 water, and the UK drinking water approval.
Yeah. So we have everything that we need on the other ones we are working.
Good. So what are we talking about next time?
Yeah, same time, same place in a week.
Wastewater treatment.
Today, yes, wastewater and oil removal. Yes. Okay. Biologic of Sandfill again comes first. We talk about backwash velocity, a little more details. Hydrocarbons, oil removal will be one of the subjects we talk about, and of course some case studies around these wastewater and oil and hydrocarbons removal.
Okay, let's come to Q&A.